Hello everyone, welcome to the next lecture on the infinite series. Today we will discuss about Cauchy integral test for the infinite series. Myself Dr. Harish Garg. You can simply follow my YouTube channel for finding the various lectures on the mathematics 1. What we have discussed so far, we have discussed all those testing of the testing for the convergence related as a nth term test, partial sum sequence, geometric root ratio and here. So in this lecture we will cover about the Cauchy integral test and its various examples. If you are interested to watch my previous lecture, you can simply follow my YouTube channel, and the playlist is my mathematics 1 where you can see all those previous tests for the convergence for the infinite series available in this lecture. Now as we will try to cover all these questions, but you all knows what is that this series is my convergent by using the geometric series test. This series is also convergent by the geometric series test. This series is a divergent by using the P test and so on. So we already discussed the various questions in our previous lecture, but we will cover the same questions now you are using with the Cauchy integral test. I will try to solve the few questions from this, and the rest of you can do it by own. What is the statement of the Cauchy integral test? If you have the infinite series which is a positive, make sure all the terms are my positive. Fine. Then if you prove that this term an, if I call as f, is my positive, is a continuous and it's a decreasing function of the n, whatever the domain is my here, then the behavior of this series an and the integral term are same. Means if this is convergent, then this is convergent. If this is divergent, then this is divergent. Moreover, if instead of this interval, that is a n comma infinity, if you take n is 1, then the still results hold for the same. Or instead of this you can take 10 to infinity, still results hold. You can take 401 to infinity, still results hold. Why? Because we all knows if you take this series here and if you take this series n varies from 100 to infinity of an, both have the same convergence or the divergence. Addition or the deletion of the finite number of the terms does not impact on the behavior. You can see the proof of this Cauchy integral test I already explained. You can follow this playlist where you can find the lecture in this video. Now I will explain you how you can solve this one. So examine the nature of this. First of all, if you apply this as a geometric progression test, that is by using this lecture, if you are using this geometric series test, you can see clearly what is the common ratio. It is 1 over 10, less than 1. So this series is my convergent. Fine. But if you apply the root test, what is the root test is if you take 1 over n, limit n approaches infinity. So what is the an of this? Again it is a less than 1, it is again a convergent. You may apply as a ratio test. So if you think an plus 1 over an, what is the an plus 1 over an? It's a 1 over 10. Again less than 1 is a convergent. So by any of the tests you will get the convergent series. Now I will try to solve this test, this series by the integral test. What you can do, whatever the function is given to you, you can take as a f of x, where x is my greater than or equal to 1 to infinity. Then your target is to prove these three properties for this f. Firstly, can you say this fx is my positive? Whenever x is my greater than or equal to 1, this number is always positive. Fine. Second one is whenever x is my greater than 1, this is always a continuous. So first two properties are easily satisfied. How you can prove that decreasing? I can start with the derivative, and our target is to prove it's less than 0. What is the derivative of a raised to power x? You all know derivative of a raised to power x is a raised to power x and log of a. So it is my a raised to power x log of 1 over 10. So what is the log of 1 over 10? It is minus log 10. Log 10 is my 1. So which is my here. So clearly say this is my less than 0 whenever x is my greater than or equal to 1. So this number is always less than 0 for all x greater than or equal to 1. Hence, the condition of the Cauchy integral test is satisfied. So all these conditions satisfied. Now this condition is satisfied for greater than equal to 1. So now my integration will be here. Our target is to find this limit. If I found this is my finite, then this is my convergent. If you prove that this is my infinite or does not exist, then we can say this series is my divergent. Fine. So now what is the integration of a raised to power x? It is a raised to power x divided by log of a. So what is that? It is a raised to power x divided by log of a into derivative of minus x. So this is my 1 to infinity. Now I can substitute the upper limit. What is the infinity? Is a 0. What is the lower limit? Is 10 raised to power 0 minus 1 over minus 10 log of 10. So what is that? It's come to be 1 over 10 log of 10, and which is a finite number. So therefore, if this is finite by the Cauchy integral test, this series is my convergent. Look at this another one. Again, if you apply the root test or if you apply the ratio test, you will easily get that this is my divergent. Fine. Now what you can do, you can start with the f of x, that is a ln x over x. X is my greater than or equal to 2. Then your target is to check whether f is my positive. Whenever x is my greater than or equal to 2, this is my positive, this is my positive. So this is my always positive. Whether it's a continuous or not, because we all know ln of x is always a continuous function. 1 over x is also the continuous function for all x which is greater than of 2. So therefore this function is my continuous. Then you can find the derivative. How you can find the derivative? It's a u over v x into 1 over x minus ln of x. So it comes to be 1 minus ln x over x square. So can you say this is my less than or equal to 0 for what value of x? So clearly says we all know ln of 10 is my 1 and ln of 11 is my 1 point something. Fine. So what is the meaning of that? Whenever x is my greater than or equal to 10, this function is my decreasing. So therefore all those properties are satisfied for the case greater than or equal to 10. Then your target is to evaluate greater than or equal to 10 instead of greater than or equal to 2, because this condition is satisfied for only 10 to infinity. Now how you can integrate them? It's very simple. If you substitute ln x is my y, then 1 of x dx is my dy. So this integration becomes my y dy, that is y square over 2. So y I can again substitute as ln x square divided by 2. So this integration is my ln x square by 2 over the limit 10 to infinity. So now if I substitute ln of infinity, what is that? It will goes to the infinite. So what is the meaning of that? By the Cauchy integral test, this is my derivative, because this is not a finite number. Look at this another one. If I consider f of x is, again you can see if you apply the GP test, what is the common ratio is e raised to power minus 1, which is less than 1. So therefore this series is my convergent. You may apply here as a ratio test, that is an plus 1 over an. Clearly say this is a less than of 1. You may apply here as a root test. What is that? An of 1 by n. It is e of minus 1, which is less than 1. So either of the case you can get as a convergent. So you can solve this problem by either of the test. But since today's lecture is an integral test, I can solve the same problem with the help of integral test as well. So if I consider this, x is my greater than or equal to 1. Now whether, because whenever x is greater than or equal to 1, this number will always be a positive. So therefore first condition satisfied. Exponential function is always a continuous. Second property also satisfied. What is the derivative of this? It's a minus e raised to power minus x. So since e raised to power minus x always positive, this is less than of x for all x over the domain, because that my domain is greater than or equal to 1. Now since all these three conditions are satisfied, so therefore this condition is satisfied for all x, my domain is 1 to infinity. So I can start from the 1 to infinity. What is the integration of this? E raised to power minus x over minus 1. So what is the integration? E of minus infinity is a 0, e of minus 1 over, so what is that? It is 1 over e, which is a finite number. Once is a finite number, it means this is convergent, hence the series is convergent by using Cauchy integral test. Okay, let k is the positive real number, show that the series is convergent for our, we all know this is a p test. So how you can prove the p test? By using the Cauchy integral test. Again, the rule is similar. I can consider this is my here, where x is my greater than or equal to k. K can be any real number. Fine. Is it a positive number? Yes. Is a polynomial? Is again a continuous function. 1 over the polynomial is again a continuous function for all x greater than of the k. If you find the derivative, because this number is my positive, p is my positive, so it is always be less than 0. So this is my decreasing here for all x greater than or equal to k. Then we can integrate from k to infinity. Now here if you substitute the value of the infinity, it will be my here. So this will be 0, this will be infinity, depending upon that whether this number, if I consider 1 minus p is my less than 0, so that means it is negative. So it means this value will be negative. So it means it is a 1 over infinity goes to the 0. So that's why we have considered the three cases. Either p is my greater than 1, p is my less than 1, or p is equal to 1. When p is my greater than 1, then this value will be my less than 0. Fine. So if I substitute here, what is my this integration? This integration becomes, when you substitute infinity, this is my 0, and then when you substitute k, it is k of this value. So since k is my positive real number, so this value is my finite. Fine. So you can say this is my k of 1 minus p, k of 1 minus p, which is a finite number. On the other hand, when p is my less than 1, then 1 minus p will be my greater than 0. So 1 is a positive number, like of x cube, like of x square. So if I substitute infinity, then this integration will be my goes to infinity. That means this is my divergent. Fine. Then it will be my divergent. When p is equal to 1, what will happen? This is my something over infinity. We can't solve that. So I can substitute here. When p is equal to 1, then your integration will be 1 over x dx over the limit k to infinity. Fine. So what is the integration of this? It is a ln of x over the k to infinity. So when you substitute infinity, it will be my infinity. Fine. So now what you conclude that? So it means this integration is my finite when this is finite when p is my greater than 1. So therefore by Cauchy integral test, this series is convergent when p is my greater than 1. Whenever p less than 1 or is equal to 1, both are my divergent, and this is the required proof of this result. Okay, look at this another one. So how you can solve? I can simply take f of x is my here. Clearly says this is my x is greater than or equal to 1. Clearly says this is my positive. This is my continuous function, because exponential function is always continuous. Now you can take the derivative. If you take the derivative, you will get here. Can you say this number is less than 0? For what value? Only when this part will be my less than 0. And clearly say this is always less than 0, because my domain is here. So if I take x is 1, so its value will be e1 minus e square, which is always less than 0. So we can say this function is less than 0 for all the values of the x in the domain. Domain is my this one. Fine. So now the conditions are satisfied for this domain. So I can solve this as 1 to infinity f of x dx. How you can solve? I can simply take e raised to power x is my t. Fine. Then what is my x? Then e raised to power x dx is my d of t. So this integration, when x is equal to 1, t will be my e. When x is infinity, this is infinity. So this is dt over 1 plus t square. Fine. What is the integration of this? This is nothing but tan inverse t over the limit 0 infinity here. What is the tan inverse of infinity? Pi over 2, and this is my tan inverse of e, which is my finite number. Fine. So once is a finite number, it means this series is my convergent. Hence, this infinite series is also convergent by the Cauchy integral test. Okay, look at this another one. Again, you can consider f of x is my here. What is that domain is? For all x is greater than or equal to 1. And clearly says it is a continuous, it's a positive, and the derivative will be here. So what is that? If I take x is greater than or equal to 1, I can see when it will be less than 0. We can see what will happen if x is equal to 1. It is 1 minus 2 into 1. Tan inverse of 1 will be my pi over 2. It is 1 minus pi over 2. Pi over 2 will be my 1.57. So clearly say this is my less than 0. So which is a less than 0 for all x which is greater than or equal to 1. Hence it is my decreasing for all the values of the x. For all x means whatever the domain is my greater than or equal to 1. Now you can integrate this. How you can do that? Again, I can simply take tan inverse x is my say y, 1 over 1 plus x square dx is my dy. So this integration becomes 8 is my outside, this is my y, and this is my dy. Fine. And when x is 1, y will be my pi over 4. When it's a infinity, it is my pi over 2. So what is that? It is 8 times y square over 2. So pi over 2 to pi over. So clearly say when you substitute upper and lower limit, you will get as a finite answer. Or you can also write this integration is 8 is outside. This is my y square. Y is my tan inverse. So this is tan inverse x square divided by 2. So that is the same thing for. Now if you substitute infinity, it's my 4. If you substitute infinity, it is my pi over 2. And when you substitute 1, it is my pi over 4. So which is my finite number. Hence by the Cauchy integral test, it is my convergent. Look at one more example. Again, I can take f of x, which is clearly a positive number. Its exponential series is always the continuous. And if you take the derivative, it's come to be my here. And because of this negative, it is always less than 0 whenever x is my greater than or equal to 1. Then we can find the integration. How you can do this integration? If I take e raised to power x is my t, then x will be my ln of t, then dx will be my 1 over t dt. So this integration becomes 2 over 1 plus t into dt over t. When x is 1, t will be my e. When x is infinity, it is my infinity. I can take 2 as the outside of the integration. This will be my here. How you can solve this integration? I can do the partial fraction, this, and 1 plus t. Fine. So when you take t is a 1, this is my minus 1. Now what is the integration of this? It will be my ln of t or log of t minus log of 1 plus t over the limit this. Or I can also written this log m minus log n. It is t over this value. Fine. What is the infinity? It's the infinity over infinity form. So I can apply the L'Hopital rule. This. So what is the ln of 1 is 0. So either you can write here as a log 10, then you have to written as a log base, otherwise you can written here is instead of ln of 10. It's on your choice. So what is that? If you substitute infinity, it's my ln of 1 minus, and then e will be my here. So this value will be my 0. So this value is my here, which is a finite number, hence it is my convergence. Look at one more example. Again, you can take f of x is my here, where x is my greater than or equal to 0. Clearly says that because this is a positive value, this is always a positive, so the product of 2 is my positive. First property satisfied. X is a polynomial, is a continuous function. Exponential is also the continuous function, so the product of the two continuous is my continuous function. And if you take the derivative of this, you will get this term. Clearly says this will be less than 0 whenever x will be my here, that is root 2 by 2, 1.414 divided by 2, that's a 0.707. Fine. That means you can integrate over this 0 to infinity. How you can do that? If I simply take x square is my t, then 2x dx will be my dt. So what is the integration of this? 0 e raised to power minus of t dt. When t is x is 0, t will be 0, and here divided by 2 I can return as a outside. What is the integration of this? It is e raised to power minus t over minus 1. So when you take infinity, e raised to power minus infinity is a 0, and when you take 0 is a 1. So what is the right answer is half, which is a finite number, hence this series is also convergent by using the Cauchy integral test. Look at one more example. Now if you consider the f of x is my here, clearly says it is my positive for all x which is my greater than of 2. Fine. Then you can find its continuous also. You can find the derivative which comes to be here, and clearly says this is my less than 0 always for all x in the domain. Now you can integrate this. How you can integrate this? If I take ln x is my y, 1 over x dx will be my dy. So this integration becomes my 1 over y dy, or you can say this is again ln of y. I can substitute the y here, or otherwise you can change the limits. When y is equal to x is equal to 2, it's ln 2, and otherwise you can substitute here is ln of x. Now the limits is my 2 to infinity, or you can substitute limits of the y as well. Now when you substitute infinity, it is ln infinity is my infinity. Fine. So you can see it is infinity, hence this series is my divergent. So this is a simple way you can solve the Cauchy integral test. These questions are exercise for you. You can try to solve these 15 questions and let me know if you have any problem in your these 15 questions in the comment box. These are the answers. You can easily verify it whether this series is convergent or not. For example, here you can clearly say that by the nth term test is a divergent. It is also divergent. I hope you can simply learn the tricks. We will see the next lecture on the Leibniz test. Till then, you can simply follow and share my videos with your friends. Best of luck, students. Happy learning.